In this episode, I plan to go over methods of evaluating regression models. So for regression problems, where we're building a model to predict numbers, such as a house price or temperature, we can use the following metrics to evaluate our model: mean squared error, root mean squared error, mean absolute error, R-squared score, and adjusted R-squared score. So let's start off with the mean squared error. So the mean squared error is given by the following formula: 1 over n times the sum from I equals 1 to n of yi minus y hat I squared. So here yi is given as the actual value which our model is trying to predict, y hat I is our model's predicted value, and lastly n is the number of test examples. So let's now go on to see how the mean squared error is calculated. So here we have some test data, with the black points representing the actual values and the white points the predicted values. So the mean squared error is given by the following formula. So here n is equal to 3, which is the number of data points in your test set. So let's take a look here at y1 is equal to 11. Our model predicted that y1 is 3, so the error is given by 11 minus 3, which is 8. Note that all of our predicted values lie on this regression line here. For the second point, we have y2 is equal to 4, whereas our model predicted that y2 is 7, and so error is given by 4 minus 7, which is minus 3. And lastly, for y3, we have an error of 1. So now we sum up the square of each of these errors. So here we have 11 minus 3 squared, plus 4 minus 7 squared, plus 11 minus 10 squared, and then we take the average of these errors, and so we divide by 3. So you might be wondering, why do we square these errors? If we didn't square the errors, and let's say for example we just sum them up, for the first two errors here we would have 8 minus 3. So in this case, our positive error 8 would be reduced by our negative error minus 3. If we allowed this to happen, the negative errors would reduce the positive errors. Ideally, we would want to accumulate all errors and ensure that negative errors don't reduce positive errors, so that we can have a final figure at the end that represent all of the errors in our test data. So calculating the mean squared error, we get 1/3 times 64 plus 9 plus 1, which is 72, giving us a final value of 24. So the advantage of the mean squared error is that the mean squared error is a differentiable function and can be used as a loss function which can be minimized. I would recommend you guys to watch the video on gradient descent to get an idea of what a loss function is. Some disadvantages of the mean squared error are: the error can be quite difficult to interpret. So for example, in the previous slide, we calculated a mean squared error of 24. But what does that really mean? Is it good? Is it bad? So what value of mean squared error is considered as acceptable? The mean squared error can also be affected heavily by outliers. So remember that we're taking yi minus y hat I and we're squaring this. So for example, if we were to square an error of 1, this would give us 1. If we were to square an error of 2, this would give us 4. And let's say, for example, a lot of our errors were around 1, 2, or 3. So here we would be adding up 1s, 4s, and 9s. So let's say, for example, we had one outlier which had an error of 10. If we were to square this, we would have a value of 100. So adding 100 to these 1, 4, and 9s would have a huge impact on the mean squared error and wouldn't really be a fair representation of how the model performs on most of the data. Next, we have the root mean squared error, which is simply just the square root of the mean squared error. So this here is equal to the square root of the mean squared error. Some advantages of the root mean squared error is that it is differentiable, like the mean squared error, so it can be used as a loss function to be minimized. It also shares the same unit as y. That is, if our predicted values are in the hundreds, root mean squared error would also be in the hundreds, so it can be easier to interpret than mean squared error. A disadvantage, however, is as with the mean squared error, root mean squared error is affected by outliers, which may show worse model performance than if the model was fitted on data excluding outliers. Although we are square rooting the final value, since we're still squaring errors, that is, we still have this yi minus y hat I squared in our formula, outliers would still have a large impact on the final value produced. However, square rooting this mean squared error helps reduce the final error produced into a reasonable scale. That is, it shares the same unit as what we're trying to predict. We also have the mean absolute error, where instead of squaring the errors, we take the absolute value. So this essentially just turns the negative values into positive values. So for example, the absolute value of -2 is equal to 2. An advantage of the mean absolute error is that because we do not square the errors, it's not affected heavily by outliers. A disadvantage, however, is that the mean absolute error is not always differentiable, and therefore, in some cases, cannot be used as a loss function in regression models. So we also have the R-squared score to evaluate regression models, and this takes the following formula. So as before, yi is the actual value, y hat I is a predicted value, and here y bar gives the mean value of y, which is what we're trying to predict, and n the number of test examples. So the R-squared score takes a value of 1, indicating best model performance, to a negative number, which indicates poor model performance. So let's see now why that is. So let's say, for example, our model has 0 errors. So if that's the case, this numerator here would equal to 0, and so we would have R squared is equal to 1 minus 0, which is simply equal to 1. So with a model that makes no errors, we would get an R squared score of 1. Let's say now, for example, our model was quite basic. It decided to predict every value of y as the mean value of y. So that is, every predicted value y hat I is equal to y bar. So if that's the case, the numerator is the same as the denominator, and so we would have R squared is equal to 1 minus 1, which is equal to 0. So a model that isn't very different from just a basic model that predicts the mean value for each observation would have a low R squared score of 0. And for a model that performs worse than a model that predicts the mean value for each observation, we would get the numerator here to be larger than the denominator, since the overall errors as a result of the model's prediction of y hat is larger than the model where we're predicting the mean value for each observation, and so the numerator is larger than the denominator, and in this case we would get 1 minus a value larger than 1 minus a value bigger than 1, which would then give us a negative number. So the advantage of the R-squared score is that we can compare models more easily than mean squared error and root mean squared error, since mean squared error and root mean squared error can vary massively when different scales are used. Whereas, R squared usually takes a value between 1 and 0, as you're not really going to find many models as worse than a model that just predicts the mean value for each observation. A disadvantage, however, is that we can overfit our data by including many variables in our model, such as polynomial variables. Models which overfit our data are not penalized and would have a very high R-squared score. So for example, let's say we produce a model here that doesn't really capture the general trend of the data, but is very complex and manages to make no to very little errors. So in this case, we would have a very high R-squared score, or very close to or equal 1, but this model clearly overfits our data. So a high R-squared score doesn't necessarily mean a good model in some cases. We also have the adjusted R-squared score, and this is given by the following formula. So here R squared is the R-squared score, K is the number of independent variables, so these are the number of variables that we'll be using to predict our target outcome, and we also have N, which is the number of test examples. An advantage of the adjusted R-squared score is that it has a degree over the R-squared score, since the adjusted R-squared score penalizes the addition of too many variables in the model. So if we look here at the formula of the adjusted R-squared score, if we include too many variables in our model, which may lead to overfitting, we would expect K here to be quite high. So now increasing K, that is increasing the number of independent variables in our model, would decrease the denominator since we are subtracting K, and as a result we would get a larger overall value here. And so increasing K increases this overall value, and so we would get 1 minus a larger value, which would reduce our adjusted R-squared score. So this can help indicate if a model is overfitting with a low adjusted R-squared score. A disadvantage, however, is that models with bias can still have a relatively high adjusted R-squared score. So for example, this model here underpredicts and overpredicts the data at certain points, showing bias, but may still have a high adjusted R-squared score. So now that we've looked at some of the metrics used to evaluate your regression model, this is what I would recommend. First, split your data into training and test data. So here I would recommend using more training data than test data. So let's say, for example, 80% training data and 20% test data, but you can use different ratios and see how that has an effect on your model's performance. We can then use the R-squared score on the training data or adjusted R-squared score, and also check this value for the test data. And then now we can compare these two values. So let's say, for example, we see a high R-squared score on the training data and a low R-squared score on the test data. That is, our model performs better on the training data than the test data. That can mean that our model is overfitting our data, so you may want to remove some variables. If we find that our model performs poorly on the training data, that is, we have a low R-squared score on the training data, this may be due to high bias, or you may want to include more variables into our model. I hope you guys enjoyed watching and learned something new. I hope in the next episode to go over evaluation metrics of classification models, and I hope to see you guys there. Thank you for watching.